Okay, welcome back. I know what is this a video. I'm just gonna do math exercises. Let's go to Teams. Yes, and just have. Oh, I think I need to download them, right? Okay, it takes 20 years to open it. But let's go to my downloads. Unless like, do we have do we have anything in here? What do I have in here? I have a book. No, I need recitation. Yeah, I am trying to solve this exercise. Yes. Let's open this. Oh my god, just need the PDF. Yes. I just have exercises I need to solve here. Okay, so I'm doing this one. Okay, someone wrote me for some reason, but not right now. So let's just try to solve this. So the point is, a person is lost in a cave and stands at a junction where he can choose between three paths to proceed. If he chooses the first path, he will come out of the cave in 1 hour. So let's open my obsidian. So yeah, game bar. I don't need it. So it's open. Oh well. And now I have now I have I need to do my homework, I guess. So I have let's call it probability theory and just have homework, right? Make a new one. Let's call it problem set 10. Let's just proceed with it. Yeah. Okay, now let's see where the problem is. So I've done the other exercise, so I'm gonna go straight to 12. Just do this. And so we have a person and it's lost in a cave and stands at a junction where he can choose between three paths to proceed. So we can choose between three paths. If he chooses the first path, he'll come out of the cave in 1 hour. Okay. If instead he picks the second path or the third path, he will return to the junction in 2 hours and 3 hours. So we have like the normal you have the uniform distribution because each path is likely to be picked, right? So, well, the way I solved it I think in the beginning was because you have 3 paths, right? 3 paths, and this is 2 hours, and this is like 1 hour. This is like 3 hours, right? And this two sends you send you back like this. You send you back, and this one, hallelujah, you get out, and out, and then this two like send you back, right? So send you back, and my point is that it is a uniform distribution. So probability of this, of let's call it 1, is equal to 1 over 3, and then the probability of this two happening overall is like the probability of this two happening is p over 2. So like the probability of 2 and 3 happening is equal to 2 over 3. And now the idea is that you have like a geometric distribution. Now the idea that our the waiting time. So what do we need to find? The expected time. So what we expected time in which we will come out of the cave, the time it takes to come out. So we have x, which is defined as the time, or tilde, or just defined as the time it takes to get out of the cave. And then you have so we need the expected time of x, time to get out of the cave. We don't know this, and what we have next is 2 hours and 3 hours respectively. Okay, suppose he returns to a junction, he forgets his previous choices and picks a path uniformly from the 3 options. You see, you pick a path uniformly, so this is how uniformly distributing. That's why this is 1 over 3, and the probability of this 2 is like 2 over 3. And how do I calculate the time? Well, in my point is that how I thought about it is that you have the idea is that for these two cases, so if you miss, it means an average, because these two have the same probability. On average, you will have you will wait. On average, here you will wait 2.5 hours, right? Here you will wait 2.5 hours, and here you will wait 1 hour on average, because you only have this, right? And the idea is that you will go back until you hit 1. So in a sense, it's like we'll define why like getting out, right? The numbers, let's call it the number of times till I I rolled, I picked till I got out. And the point is that you can like I treat 2 and 3 as one thing, and what that does is that you roll it's like this is a geometric distribution, and then it's a geometric of 1 over 3 for success. Write it like this, and the point is it doesn't know tilde, so we can just do this, or we can just wait a second. I think this is a problem. Yeah, it's not letting it work. It doesn't matter. So now the point is that it comes with tilde. So this is what we have here. But we know we need the tilde, and it doesn't tilde. How do I write the tilde here? So y tilde 1 over 3, and I cannot write the tilde for some reason. Okay, how to write tilde in latex? Very funny. How to write tilde in latex? What? Sim. So not good. Why can I just? And then this thing that the auto completions. Bro, I hate this auto completion. I need to write sim. I could have just written sim. It auto completes it. Okay. So you have sim, and then so we have why is here because and then the point is that the expected value of x is equal to expected value of x given y, is that it takes this much time, right? Given y, because this x and x given y, what x given y tells you is it tells you what the x given 1 tells you. It tells you given that you roll, given that you picked several times, given that you picked 3 times, or given that you pick y times, how many times, how much time did it take? So given y, and then the point of this, the idea is that I don't know. So if this tells you give you pick, so how much time, and this is equal to I have no idea. I'm very dumb right now. Well, I know how you can solve it directly, because from this, I'll just solve it directly. Well, from this I know that so on average, because this is like a geometric distribution, I know that the expected value of y, let's call this, I know that because therefore y is this, so I know that the expected value of y, so I know that the expected value of y is just 1 over, it's just 3, is 1 over the fraction, so it's 1 over 1 over 3, 1 over probability. So you expect, this tells you that you expect to pick 1 after 3 turns. So at the third turn, you have to pick 1. So you leave at the third turn. So you expect to have 3 turns, right? So what this tells you, have like 2 or 3 in here, and then you get 1. Or you can have 3, 2, 1, or 3, 3, 1. So the point, you can have 3, 2, and 1. And then, so I'll just do 2, 3, and 1. And then the point is that how much does this take on average? Well, how much time does this take is that 2 of them are bad, plus 1 of them is like good. So you have for this 2, on average you have 2.5. So expected value of that first part is 2.5. So you have 2.5 times 2, and you have plus 1 hour, because the last one to get out, it takes you 1 hour to get out, and this is equal to 5, and it is the right 6, and it is the right solution, I think. Yeah, it is. The solution is 6. But the point is, how do we express it? We want this to be expressed using the what's the name? Like we have, if I open the recitation code, let me see where it's in download files. I have a summary. And if I open the summary real quick and I go to like lecture 17 or I don't know, yeah, law of total expectation. I think we need to use something like that. And the point is that this thing, how do I express is using this, right? Something like this. So I really have not, like, I get the point, because this is like, if I remove this at all, like the expected value of x is the expected value of tools, how many tools you get, and then the expected value of how many tools you get, times 1 over 3, I guess, times, yeah, the expected value, because x, how the table of x looks is like, how do you draw a table in like in Obsidian? Let's just activity. Draw a table in LaTeX. Draw markdown table in Obsidian. Just markdown table. Yeah, this is what I wanted. And then the point, how does the x look, is that it has so what the x has, so it's x, and then you have the function of p of x, I guess. Can I do this here? I hope so. And then you have p of x, the mass probability function, p of x, and then let's see how that looks. I think I have a table, right? I have like a table plugin. Yeah, but, can I just remove it? I don't need it. Okay, can I just remove it? Close. Okay, can you close it? Close. Just close. I just want you to. Yes, nice. Well, so now the point is that you get. How many times can you wait? You can wait 1 hour, right? You can wait 1 hour. You pick white. The number of times I picked. What is x? The time it takes to get out of the cave. Well, it can take 1 hour, but it can take. Yeah, the time it takes, it can get 1 hour, 2 hour, I don't know, sorry, right? You cannot think like this. It can take 3 hours, but you cannot think like this, right? Like, it doesn't make any sense. Oh, I'm recording, yep. So you cannot think like this, so what? It can take many hours. So the point is that you give, so you cannot like, the time it takes to get out of the cave is just like, it can take 1, 2, 3, and you have no idea how to give them as function. So what I think you do, is that you give x given y. So let's suppose you roll the, oh, this doesn't work, so I should do this. Yeah, this works. Suppose you give x given, or we can just do LaTeX in here. And so let's suppose, I suppose x given y. So given that the number of times I picked till I go out. So this solution was just immediately, but let's do it like mathematically. The way you do it mathematically, you give x the times that it takes to get out of the k, and the number of times I pick till I get, like, the numbers I pick till I get 1. I get 1. This is just a geometry, so y is just a geometric distribution. And then you have x given y, just give what you picked y times how much time did it take. Yeah, given that you picked y times, because it tells you till you get 1, that's how much you have picked, how much time did it take? Well, if you picked only 1 time, but what? Well, I'm pretty dumb, I think. Something is missing. So let me just look at like what we did in class, because oh my god, my brain is what? Okay, this seems very weird. This is actually pretty weird. What they did is pretty weird. Like what we did in class looks pretty weird to me. Yeah, what they did looks pretty weird. So I think I'm gonna ask her 12 means. 12, pretty weird to me. But like, I know it's 6 like this because it makes so much sense, right? So on average, if you get the bad path. So the point is that, or you can just say, let's say x is the time it takes to get out. Okay, well, if you pick 1, use 1. No, the average time, you don't pick 1. The average time is, it can be 1, it can be 2.5, and then the probabilities differ, right? Because it's a geometric distribution. So, I don't know, I think I was in the right track here, and this is so much better solution than what I see here. So what I'm doing is that, well, you know, Okay, this is a good one. Given that the number of times I pick is y, this is how much time it took. So I can do x given y, because x given y, so x given y can have, yeah, it can have different values. So it can have where there are all y minus 1 are 3, and then 1 minus 2 are, like, you can have you can have like 2, 2, 2, 2, 1. So let's suppose this is y, right? So x given y is that. So it's like a hard distribution, though. It's not like an easy one to explain. But I get that, like, I can do it immediately, and I have no idea how to express this mathematically. Because in a sense, this is not 2.5. This is, there are values 1 times, it is 2 times 1 over 3, right? And it is plus 1 times 1. This is 1 to get out. This is 1 over 3, this is 1 over 3, and this is 3 times 1 over 3. And then this should be 6, I think. Plus, how much is this? Let's just, I know I can calculate. Okay, this is 1. So 1 plus 1 over 3. No, it's no way. Plus 2 over 3. This is just, so I don't know how to, this is bad. I don't know how to explain it mathematically. Like, I get how to find it real quick. I mean, this is just, yeah, it is just a geometric with 1 over 3. It's just a geometric with 1 over 3. You don't even need the x. Or you can think with x. No, you don't need the time it takes. You just have the number of time I pick till I get 1, right? So I guess let's draw y. Let's draw how y looks. The way y looks. Let me just save this for later. So I can just like, I can just do this, and then I can have this with y. Then the way it looks is that that I get 1 roll. Yeah, so this is just geometric. So, and then how the way geometric behaves is that, let me get the paper real quick. It is the range of geometric. What is the range of geometric? Range of geometric is from 1 to infinity, right? So the probability that you get 1 in the first time is just 1 over 3, and then you, this is like geometric distribution, right? Why did they thought they've done this? Because I don't need this part. Okay, so I have 1 over 3, and then I have this is like 2 over 3, or this is like, yeah, it is, I get something else, like I get 2 over 3, and then times 1 over 3. It's just geometric, right? Doesn't matter. I should do this. Oh, what do I do? Oh, I removed it. So, real quick. Yeah, it's just a geometric thing. Yes, and dot dot dot. Well, this is just y. Yeah, why should I draw y where I just explained that y is a geometric of 3 with probability of winning 1 over 3. Yeah, it's just a geometric, but it is scaled, right? Yeah, it's just the expected value of geometric, and then that expected value is changed. Right, so you don't need x given y. I don't know why they put it here though. Like, we're learning about the theorem, and then the theorem is not even applied in here. So point you just have y, and the expected value of y is 3. And then I know that the expected value of x, expected value of, oh, I need to x, the amount of time needed to get out. I don't care if it is right. Yeah. So the number of times I pick till I get 1, right? And then the expected value of it is equal to 3. So we just have, in a sense, I just have the expected value of x, and this expected value of x is just equal to the expected value of x. Yeah, it is just expected value of y, I guess. Expected value of y minus 1. So y minus 1 times 2.5 plus 1. It is, and you can see that this is 2.5, because you can get an average. You can get, for example, you can get just like a binomial, right? You can get to 2, and then you can get to 3, 3, 2, you know, the average they're like equal to each other, so on average this gets like, so this like gets, for example, 4 hours, this is 4.4, it's 2 plus, okay, what do? This is, yeah, 2 and 3, so this is 4 hours, this is 5 hours, this is 5 hours, and then this is like 6 hours, and on average this is like 2.5 times 2, right? 2.5 times 2, which is 5. That's the average. You can see it just averages out. So yeah, it's just like 2.5 y minus 1 plus 1, and this is equal to 6. You don't even need to draw this. Why is this like this? What? Oh, interesting. So you need to wait. Let me do this. Ah, because of this, that's why. So I can just... Yeah. Oh, big mistake, but yeah, and I don't get why. Can I just do this? Let's see, I hate this. Okay. It's just too big when you compare. Let's see, how to make the latex. Text and math, oh my. Let's go to my ACS snippets real quick so I can put this in. I can change the appearance, it's too big. Appearance, and I have my snippets. If I can open this with Notepad and not with show more options. Oh, open with, where is open with? What am I open with? And here, let me add, if I save it, how does it look now? Oh my god, it makes it bigger. Okay, so let's do 80%. Okay, this looks great. So now we have it. Well, I do this, right? So why is it not adding wait, did I change anything in the settings so it doesn't do that? Okay, this was the problem. So now it should, yeah, it does. So I don't even need this. But then I don't need the 80% there. Oh, I can make it 100%. I can have it for later when I need it for something else. Control save. Can just do it beautifully. Tab. Oh my god, this tab is so big. This works. So I think this is a solution. Well, I will talk with my professor later, because this like looks so much easier to me as a solution than the other ones. So it took me 30 minutes to finish that, and I'm not done with nothing. So let's just do things more quickly now. I probably have to turn on the lights here because I can't not see anything. But let's go. So we have let x and y be independent. So let's go here, and we have 13, right? Oh, I think I can type a line in here, right? This works. I have 13, and then we have let x and y be independent random variables. For find the regression function of the we just need to find the regression function, and they're independent. So to find the regression function, well, we know from the theorems that the regression function, how you like do the regression function, is that you have so you have e of v. So the idea is that you need to integrate some. So to find the regression function is that you can just like put the values 3x in here, 3x plus 2y, and then you have given 2x minus y, right? And then oh, so these are independent, right? But these are not because they're not independent in themselves. Oh, but this is x is 2x minus y, and then you have 3x plus 2y. I thought we're gonna do like something like factor it and you get x minus y, right? But you cannot factor it. Well, we need to think apparently. I have no idea. I think we need to turn on the light because our eyes are getting fried up right now. Oh, and I'll also get some water. I think this looks better. Yeah, well, I think I got something here. So the point is that 3x, right? You can do 3x. You can do it as you can do like 2x, right? Minus y, and what you get is that you're left with an x, and you get plus 3y, right? You get plus 3y. So this thing is. So 3x plus 2y is equal to this. But it's still the same because you're finding x plus 3y now. So I literally did nothing. Maybe we can use that they are independent and they are just normals. Well, generally speaking, this is just equal to the integral. That is like this. From 1. Or maybe you guys like it in Desmos, probably. Let's write it in Desmos because it's way easier. So I can just like do it down here and have this thing up here. So I can just write it in this expression right here. I can just remove that. I can have this, right? So I can have this. So it's like expected value of VW is like the integral from in like the range. Should be in the range of v, right? And the integral is from in the range of v. So, and then you have from wait a second, aren't these bivariant normal distributions? Yeah, why do I just think these are bivariant normal distributions, right? Because you have 3x plus 2y, this should be. Yeah, that's just a linear transform of two normal distributions. This gives you a bivariant normal distribution. I think, yeah, bivariant normal distributions. Yeah, I can find what v is, and I can find what w is pretty easily because of this. Maybe I need to find what v and w is. But if you think about it, the expected value of this thing, so this just equal to, what is this equal to? Well, is the range of v, right? But you need the, so you have v, and then you have f of the density function of the given w, evaluated at v, small v and w. Desmos just likes putting this kind of thing in here. I can just, yeah, real quick, so I can just remove some of that. Real quick. So that might fine, I think. Yeah, and then you have dv. It's just with respect to v, dv. It doesn't just likes to put one more of those. It's pretty annoying, but you get the point. So if you look at this, I think maybe we can find this function, right? We can find this. Let's try. Yeah, we know the formula, but like, I think there should be an easier way to solve this. There's too much integrals, right? Another idea is that you have a, so you know this distribution, this is also a normal distribution with these other parameters. You also know this distribution. Somehow calculate that using that. I'm kind of mad. Well, can we find the joint distribution function, right? Can we? I don't know. Like how it is. Well, there is a formula for that, but you need to find the, no, this is like the conditional, not the joint, but you need to find the joint for that. And how do you find the joint for this? This is over this is over f of v, f of w given w. So you have this, right? First, do I know f of w? Yes, I do know f of w. Do I know fv of w? The joint distribution of v and w? Well, no, because it's a relative that this and this happen. And it just looks weird, right? Well, let's just find the normal distributions of this too. Well, what v follows is that, well, I know v is, let's write some. So v is normal of, well, we have three, we have, well, we have a formula. The way you do it is that, well, let's think about it. How would you do it? Yeah, it is this. So you see? So this is what it's saying. This is important, right? If you have y equal x plus v, then x is equal to this, then y is equal to this. You see how a multiplies this plus this. This is like mu was here, and then you have sigma. Sigma only cares, it's like the square. Yeah, it makes sense. It makes sense because if you remember is that if you have variance, because that's just variance of sigma square, right? So that's just variance. Here, this is just the variance, right? So let's say, so you have a variance now of a x plus b, and this is just well, you know, this is just equal to a squared times the variance of x times just variance of x, and then you have oh my god, I just did all the things. No, I don't know. I know you're not made for this, but it's so easy to write here. And then you have, and then it's the same idea. Now we have it's the same idea for, so expected value of x plus b is a times expected value of x plus b, and you can just put this here. So using this, I can say, right, and using this, let's say this. So stop pressing. Okay, just want to see how it looks. Yeah, using this too, we need to use this to properties. So using this to properties, we can say, derive that n is well, if you look at the exercise, it is 3x plus 2y. So if you hit 3x means that you only get 3 times 0, which is 0, and then 2 times 0, which is 0. So we get 0 for this, and then then this changes a lot. So you have 3 times, and you know they're independent. So if you look at it, you have a variance of 3x plus 2y, and then 2y, this is just equal to, because you can separate them, and they're independent, right? Because, and then the covariance becomes 0, because they're independent. This can be, this can just be, so I think they want us to find that, so this is just 9, this is just 9 plus variance of x, plus 9, that's just 1 plus 4, variance of y, so, and plus the covariance of those two. So the formula is like this: covariance of x and y, like 3x plus 2y, but yeah, this like 3x and 2y, but we don't care about that. So this is just equal to, and the variance are 1 from the distribution. So I can just write 13 immediately. We just expand it a bit. Yep. So I'll just write the calculations down here, I guess. Or I can write them up here. So you have 13 for this one. Yeah, you have 9 plus 4, and then for the next one, you see, and then we need to find the w, and w is just I don't want to divide w, and then you have sim, and then what do you have? You have 2x minus y, so you're gonna get 0 again for this, right? It's gonna be 0, and then here you're gonna have 4 minus 1 for audio, but it doesn't matter because it's a plus in here because it's squared. So you're still gonna have 4 plus 1, which is 5. Very interesting. And why do I make this big? You should make them small. It's so big. Alright, the big one makes sense. So we have this. We have derived v and w real quick. Okay, so now that you have v and w, what are we supposed to do? We just define. So how do we find the joint distribution function, right? How do we find this, like with joint 1 in here? I have no idea, like, can you really find the joint? Does this make any sense? Because if you find the joint, we know this, right? How do we find the joint of 2? They're not independent now, are they, right? If they were independent, then it's just easy. It's just, if they were independent, then it's just f of v, completely, just the expected value of v. And the expected value of v is pretty easy. 0. Yeah, but you're still going to have no expected value. So the expected value of v given w is just 0. The answer is 0, right? It doesn't even tell you. The star. Okay. You need to give a function, I guess. Just a function. It's a function of v. It should be independent. Yeah, you just use this real quick, right? Wait, I have an idea though, because of this, right? So what my idea is that you can say, what you can say. What is v equal to? V is equal to 3w. No, it's equal to, you can say, how many w's is this equal to? 3, no, it's equal to 3 over 2. 3 over 2 w, right? Plus, you can do that, right? Minus 3w or something. Not really, but you get my point. So, no, you can't. It's pretty weird. It's like 3 over 2w plus get minus 3 over 2y, and then from minus 3 over 2y, we need to add 3 over 2y plus 2. 3 over 2 plus 2y. can just make, then you can just spread this out. You can just remove this part, and then you're left with, let's call it 4, right? So it's 7 over 2. 7 over 2y, and then you get just the 7 over 2y with 2x minus 1. Actually, I cannot do it for some reason. Why is this hard? This is very weird. I don't like it. Maybe I also need some papers to write. Really? Fuck. Well, maybe I can use the other formulas, like for example, I can use this form, because this way is very hard to do this way. Maybe I can use other formulas. Ah, this is the best regression, and this is not linear regression. This is general regression line. No, I have no idea. Like, no way. Like, they are not independent. If they were, it would have been easy. How is that the product of their margin? No, I can't solve it. I'm so sad. Okay, let's go to 14. So what is 14 gonna be? Let's do this, I guess. So let's exit the number of customers calling the customer service of an ISP on a given day with a random variable x. Okay, what is x? Okay, let's do it real quick. So x is defined by the number of customers calling the customer service of the ISP on a given day with a random. So it's a Poisson distribution, yeah, with parameter lambda. So that's x be a poise. So x is the poise of lambda of this lambda parameter, lambda. I mean, let me just lambda. Yes, and then for each customer independent of others is a female with probability. Yes. So so we have indicator variable for being a female, indicator. Right, I don't know, indicator of female. I don't know actually what kind of is equal to indicator of female is equal to. So we have indicator of female, probability p, I guess, and let y denote the number of women in the queue. So we have the number of women in the queue. So let y equal the number of women in the queue. Nice writing. The number of women queue. So you have a number of women in the queue, right? You need to give the expression of y given x. The regression, I mean, of y given n, y squared given x. What is the distribution of y given x is equal to k? Is every normal distribution independent from each other? Let's ask it here. What is the covariance? How do you measure the covariance? Let's see if the covariance. Oh yeah, we have a theorem. If the covariance is 0, then the normal distributions, the joint normal distributions are independent. But how do we find that the covariance is 0? How do we know that the covariance is 0? Listen. Well, we can measure the covariance right here, right? If we measure the covariance, of 3x plus 2y, 2x minus y, 2x minus y. And what is this? Yes, we have 3x with 2x, which is not 0 because you have a variance. This is just, I think you can just 9. And then the other covariances are just 0. The other part are 0 because they're independent. The covariance between them is 0. And then you have the covariance of 2y minus y, 2y minus y just 1, so it doesn't matter if it's minus y just 1. So this is equal to, it's not the same, plus, right? So let me do it real quick. So we have the covariance in here, so you can just separate, right? So the covariance of these numbers, we have 6 in here, 1, so are just 0 because they're independent. Yeah, I don't know how to solve 13.1. Let's do 14. Let's try again. So give a regression of y with respect to x, and y was the number of women in queue, and x is the number of customers calling a day, which is defined as the number of customers calling a day. So what you have is that the number of customers calling a day, given that you know the number of customers calling a day, what is the number of women in the queue? Number of women in the queue? So you know, so it just tells you, a number of customers calling a day, so you know how many customers are in the queue. Or you can just say the numbers of, which is equal to the number of customers in the queue. And given that you know the number of customers in the queue, what is the number of women in the queue? Well, you know that the probability of having a woman is so you just have, so y is just a geometric distribution. Y is just a geo. Y is just sim, right? My mind, sim. Y is just geo of well, indicator variable of 1f, I guess. But you don't type indicator variable is no, it's not a geo, it's a binom. It's a bin. It's a binom, and then you have how many of them you have. Well, you have expected value of the number, so it's x. It's bin of x, and then you have a probability of 1 of f, right? Or you have a probability of p, I guess here, just p. Just have a probability of p. Well, this is y given x, right? Because your y given x is this. And just if you want to want y, you know, find y given x, right? Well, the expected value of this is equal to expected value of bin, which is just, yeah, this is just 1 over x. Well, no, it's just x times p. X times p. Just x times p, but well, it's just the expected value of x. Oh, it's just the expected value of x times p. Yeah, it's just the expected value of x times p, right? It's the same thing as I did right here. No, not really, but yeah, it's just the expected value of x times p, which is equal to 1 over p over lambda, because it's a poise with lambda, and then for a Poisson distribution, what is the expected value? Is just lambda, so it's lambda times p. It's lambda. Wait a second, is the expected value of x, and the expected value. No, it's so dumb. It's lambda times p. Because the expected value of x is just lambda, right? So the number of customers calling the customer service in a given day. So you have a random variables. Yes, so you know. Well, if you think about it, I give you y and x, and then I want the range of y. Binom, but the regression function depends on x, so this is just, I don't need to do that, it's just this, and then we need the expected value of x squared given x. Well, we can use the same distribution for this, right? You can use the same distribution, but you integrate with y squared and not y. So what you get is that the expected value of y squared, and you get an x. This is just equal to the integral. Oh well, let me write it here. Is the integral from, what is y? The number of women in the queue. It can be from 0 to x, right? It's integral from 0 to x of y. So y, the number of people is x of y. Of y of the and then you have a distribution. You have a binom, so you have a distribution function with binom, and so you have oh, it's not an integral though, right? So it's not an integral. So what you're finding is just the second, right? Oh well, it's not that hard, because you know that the variance of x, right? The second one, you can use a variance, is plus e of x, is equal to, I mean, expected value of y given x, the variance of y given x, and we have y given x is equal to expected value of y squared given x, right? So you know this. So this is equal to, so variance of y given x, well, it's a binomial distribution. So binomial, just, it is x is square root of x, you have square root of x minus x p 1 minus p, square root of that, but it's square, so it's a variance, so you don't need the square root at all. This, and then you have plus x p. This is just equal to, so weird, right? But it's xp squared because this is squared. This is, or I can this, right? So you have xp squared. So you have x squared p squared. So this is the regression function, though. Doesn't even give you, it just gives you a star. You don't even know the solution. Do you get the point? Well, and it says, what is the distribution y given x is k and k is greater than 0? Yeah, hell, I just solved it like this. I think that's the solution. So we go to 51. So I think we just take a small break. Oh, I'm playing that right now. Let's see. So we need to do 50. We need to do till 18, right? I just turn it into settings, and I can just go to editor and now live preview. I just do live preview, and it's more easier for us to understand. You can see. Yes, fix it. Yeah, judge my headphones, okay? I see. Oh, we are back. Oh my god. So what are we supposed to do here? Oh well. Let's see. Oh, we are at 15, right? So let's see. Let y be this and x a uniform distribution from y squared. What is the probability of? Interesting. What? Yeah, I see it. But what's the point of this? So if you go to, I think we need to go to the drawing board. So x draw. Oh, so let me put my exercise in here, I guess. Down here, and let me put my drawing up here. So what is it saying is that you have a normal distribution and x have uniform distribution in the interval from, so we have, oh my god, it's big. So we have y is also uniform distribution, and we have x have uniform distribution interval. So we have, say, y is uniform from 0 to 1, and we have x from y squared to y. So let this be y squared, I guess, and let this be y, right? So we have a y squared and y. What is the probability that p of x is smaller than 0.5? Well, to know that p of x is smaller than 0.5, what should we do? Well, we need to find the cumulative function of x, right? What is it? Well, x is it's also uniform. So x is like a uniform from y squared to y. So it is f of x. It is from you can just have a formula, but you get the point. It is yeah, it's y squared minus y, and it is, and then 0 over y, and then you have 0. This is from y squared to y, and this is from and then over y, so area over region. But this may change probably depending on where you are, because this is a distribution function, right? It's not a cumulative function. So this is a distribution function. I think if I write it real quick, maybe it's more easy. So I think we have a formula here. It's the total law of probability, I think. Yeah, law of total probability. Where is the law? Yeah, this is the law. Do we have a good one? Oh, it is just for a law. So P of A is equal to the integral from P of A given x equals x and f of x. Yeah, exactly. So we need to find the y, right? So the distribution of y is easy, because the y just has f of y is equal to 1, right? Everywhere from 0 to 1, and then 0 otherwise, and then f of x. So probability that x is less than 0.5 is equal to the integral from y squared Well, x is 0.5 means that you have the x, so the x is from, so y. What is yeah, 0.5, and it's only defined in y squared and y, so it depends what the value of y is. So it depends on the value of y, right? So what the right solution is that so y can take the values from 0 to 1, and y squared can take the values from 0 to 1. No, not exactly. If y is less than y squared, it is 1, right? If y is less than y squared, it is less. So in a sense, you have like an interval, this is y, and the y squared is smaller or equal at 1, right? So it's just like a difference between if y is here, then the gap is bigger, and then you have 0.5 in here, right? So you have different cases, you have many different cases. So you have a case where if y squared, right? So if y squared is greater than 0.5, or in a sense, if y is greater than 0.25, if y is right, square root of 0.5. Don't mind me, please. Don't mind me. 0.5, not exact, but 0.7 something, but you get the point, square root of 0.5, because, and it's the positive region, so we don't care about the negative, because y is defined from 0 to 1. Y squared is greater than 0.5, right? So if that is the case, when you have 0, this is not the, yeah, this is a probability actually, but you need to define it with respect to x, right? And then if y is, and then what do we do if y is well, if y is equal to 1, right? No, if y is 0.5, I'm lost. Yeah, the distribution is uniform from here to here. Okay, so if y is less than 0.5, then we just have 1 over this is equal to all of this. That's equal to this, because it's the area. It's equal to, well, when the distribution function is just yeah, it's like what am I doing? This is like y squared plus y over 2. And if y is, yeah, these are the two regions, right? Not really, there is one more region where it cuts it. So this is y greater than 0.25, not 0.7, 0.7 something. Then you have, so for 0.7, or the square root of 0.5, so it was somewhere here, and you don't even have 0.5, you have y squared in here, this is y. So if it is from between 0.5 and 0.7, 0.5 and square root of 0.5, then you have y squared minus 5 times over 2, because you're not applying it, you have a uniform distribution, right? So it's just a value is between the two regions over 2. Let's see how incorrect I am. And it gives you a value. It's insane. Does it give you a value? It depends. Well, if you use the formula, then you have the probability of A, probability of x, which is less than 0.5 or equal, which is equal to probability of A, is equal to the integral from, what did I say? The integral, yeah, from minus infinity, doesn't even have infinity, or test, from minus infinity to infinity of probability of A given y, because we are given y, right? So probability of x given y is x, f of times f of x times f of y d y. This is big Y. It's pretty weird though. It's pretty weird because why does it just give you a value? I think better to rephrase it better, this should be like this is f of x 0.5 is equal to f of x given y 0.5. No, given x and y. Depends on the y. Oh, I see. Oh, I understand. So I just, oh, I derived x here. you have here you have and what else do you have? You have yes, what I derived is you have yeah. So for f of x, for f of x equals 0.5, what you get is that and what you have in here is so you have minus infinity to infinity, and then what you have is what is the probability of so infinity it is well of f of x. This f of x given y. F of x. This is f of x given y. X given y. The integral is from 0 to what? Well, wait, the first integral is from 0 to x, right? It's this. And then you have plus, and then you have plus integral, and the integral is, or I can just see, right? I can just say, and then plus the integral of, well, this ranges from, where does this range? So, I think I should have written this in my text, that's why. It would have been so much more easier. Well, this is the integral from 0 to, no, it's from x to, well, this is how I, where did my thing go? What? Right, I'll just write it here. From 0 to x of y squared plus y over 2, no, over 2, right, let me just write this, and then you have dx plus, you have integral from x to x of y squared minus x over 2 dy, alright, this is dy, and this is like 0.5. Wow, dy, and not even close. But it's not even, because this is plus in here. Still not even close. I have so many other things to do. That's so sad. It is actually, what is this region? Wow, this is so wrong. My function is so wrong. Because this should be, this should be. So it is just 1 though. So this is just 1 because everything is fucking included. Yeah, it's like y minus y squared. So it's this, and my integration is completely wrong, right? My integration is completely fucking wrong. Oh. So here from 0. What? Well, it's just 1 from 0 to 1. So this is the case, right? So you have, and what's the integral? Well, you have from 1 to 1, right? So you have it to 1 to x, which is from 0 to 0.5. You have 1, and it's just 1 for a2. And then you have from 0.5, you have from 0 to 5. From 0.5 to square root of 0.5, you have respect to minus 0.5 minus squared, and then you have y minus y squared, and then greater than 0, so plus int from square root of 0.5. You take the square root from 0.5. It's just 0. And it is minus 15. Well, I finished 15, I guess. So 16. So a certain coin manufacturing factory does necessarily make symmetric coins. So it doesn't make symmetric coins. So let us denote x, the probability that the coin lands on head. X has a probability density function f of x. X equals to 6x squared. If we toss one such coin 4 times, so this is the probability that it lands on the heads exactly twice. So what we have is that we have what does denote by x? X is the probability. What? The probability that the coin lands on heads. This makes sense. Probability. It's probability the coin lands on heads, yes. Coin lands on head. X has a probability density function. How does it? What? Okay. X. So x has a probability density function. Just write it here. I can just think. 2. Yes, and it is for the region, yeah. For this region, 0 to 1, 0, 1, and well, it says not including them, so microsize is from 0 to 1. So we toss a coin, that coin we toss it 4 times, so we have 4 slots, 2, 4, well, I need to do this, we have 4 slots, So what is the probability that it lands on the head exactly twice? Well, this is a binomial distribution, so the number of heads, and y is what is y? Yeah, then that y has oh my god, y. Bro, what is y? Y is bin of y given x in this case, right? So y given x is just a bin of binomial of 4 given x. So it's binomial of 4 and the probability is x. And the question is, what is the probability it lands on heads except twice? So we have p of x. Well, we need to use the total probability theorem. Yeah, this theorem right here. No, this theorem right here, the law of total probability. So what it's saying is the probability that it lands on head twice. The probability of y equal to 2 is equal to the, well, using binomial distribution, this is equal to, and so you need to choose, is it choose? How do you write, how to write binomial distributions? Binom is called binom, it's literally called binom. We have binom, so it doesn't want to do binom. So we have binom of, what are we choosing? So we're choosing 4 choose 2. You choose 2 of them, and then the probability of x. I don't know, small x or big x. I don't know. Probability of x to a power of 4, power of 2, and probability of 1 minus x to a power of 2. So x to a power of 2. So this is what you get. 1 minus x to a power of 2. If you want to land exactly twice, well, yeah, exactly, but we don't know x, so for each x we have this formula. So for each possible x we have this formula. So we have of x dx, and then we have here we can just take the, you can just put it in here real quick. I'll just call it f of x, big x, and then we have right? And then what we have is the integral from 0, we have the integral from 0 to infinity to, no, 0 from minus infinity to infinity. I mean, yeah, I don't think it likes infinities from minus infinity, because, but what is a region of f of x, right? F of x from 0 to 1, so it's just the integral from 0 to 1, just the integral from 0 to 1 of all of these, and then all of these, yep, of f of x dx, yes, this is, and then what is f of x? We need to find f of x, yeah, it told us, so f of x is just, so generally it's like, this is like the int, it's from minus infinity, infinity of probability of a, probability of y equal to, given that x is equal to the small x, generally, then you have all of these, which is equal to all of this, and then you have f of big X, right? And you have the, okay, and this is just equal to 6x, just the 6x minus x squared, so this is just a long fucking formula to calculate, which I ain't calculating, just all of these, just like this, and I can just do this real quick, and then remove the other left though. This, and here we are. Well, it looks pretty good, I guess. Let me to calculate this. The x, and I just do MCR 4242. And this is my result, which may be very far away, but let's see. The result is 0.2571. And I ain't calculating this integral. No. I ain't maybe I write this in big one. Okay, so we got 16. We have 17, so this is 17. So this, this. We have 17. So what is the plan? So an app is regularly checked by its creator for a security bug. Let t be the time in which a security bug is detected. It is known that t has the following distribution. So we have f of t, and t is given 1, 0, and 0, right? So an app is regularly checked by its creator for security bugs. So we have an app, regularly checked, t the time in which the security. Oh, so we have t in here. So t is defined the time in which the security bug is detected. The time takes to detect, or the time in which is, like, is it t the time it takes to detect the security? Yeah, the time in which it is detected, starting from 0, because this is like a exponential distribution, right? So we have the time in which security bug is detected, and then we have this monstrosity here. So we have t, which takes t, and t maps it to this. Very nice writing of a function. This is actually losing like the, I don't know, is mapped to. And if I do this using latex, how bad can it be? And I do f of t, and you take t, you just take t, and then yeah, it looks pretty good, but I need t is equal to cases, and then I just have the cases, I just have the cases. And you have all of this squared, I guess, right? So you're squaring all this. T squared, this is t squared, squared. Yep. Aha, I made a mistake, that's why. T is good, yeah, it's just exponential. Yeah. So we have t. I think these are like harder exercises, that's why it takes so much time. So we'll delete this. So now we have a lot of this. Wait, can I tell you that? Yeah, I can. Ah, it doesn't look good though. You can look at it. Take the. Well, the point is that you have. It doesn't make any sense. You have apps. Right. Can't even see it. Doesn't look bad, does it? I'm trying to solve this one now. Yeah, it's taking too much. There are not like very easy exercises. It's like a bit different, I guess, than the others. So we have an app is regularly checked by its creators for security bugs. Okay, and let t be a time which second. Okay, so we have a time. So we know like so it's not that t has a following distribution, right? The security time can be detected, right? It's just the exponential distribution, and it can be detected randomly. So the point, the idea is that you have a exponential distribution, right? And then you start you have bugs, but it is detected, like it can be detected immediately here, and it can be detected later or later, but the later is detected. So the later you go, like it has a exponential distribution. So the point is that, so if you draw the exponential distribution function, I can just draw it, right? So it is just lambda, and I don't know the lambda here. Did we have lambda? Well, it's 2 squared over 2, so lambda should be, and this is 1 minus, oh, this is f of t? No, this is just a distribution overall, not even close. So if I just take this distribution and I draw here, over 2. It's like, let's do this e to the x, right? And so you have this distribution, and it says t greater than 0, right? So in a sense, you have this distribution right here, but can I grab it? Okay. So you have this distribution, but you have the time is greater than 0, so you have the time from here to here. So you reach 1 somewhere here, I guess. So close, you get the point. So the more time you take, the more, like here, detecting the bug at 0 time is just very less probability, but the more you spend your time, the more time you get to detect the bug. So what it's trying to say is that if it takes, for example, 2 seconds in here to detect the bug, so it says here 2, then the probability of taking not 2 seconds or hours, I don't know, but 2 units of time, suppose it's hours. If it takes 2 hours to detect the bug, then you get the probability of that be happening is 80%. The probability of detecting the bug at, for example, the first hour, it's 0.4, right? And the problem is between this time 0 and 1, the probability of an exploitation happen is 1 minus e to the minus t. So let's say here that what, I don't know, exploitation, let's say it is, oh, this is just fixed. Yeah, the probability of exploitation is fixed. So the probability of being exploited, the probability of exploit given the time, so the probability of exploit, let's call it E. And I don't know exactly how you defined it, just exploitation right now, exploitation. And then the probability of given the time t is equal to 1 minus e to the power of t is what it's saying, right? Given that you have the time t, and then we can call it big T, because it's just the probability. Well, but that's also the this is just saying that f of like e of t, and 1 minus e to t is just exponential with, it's just an exponential with the probability of lambda. What is lambda be? But it's minus t, that's why lambda is just 1. No, it's minus t, so you have minus 1. No, it's just 1. So it's just an exponential of 1, right? And I need to write the lambda as the same. It's just an exponential of 1, right? So it's asking what is the probability, so what is it asking for? So let's do this, let's take this and let's put it at t. And it's saying, and then he is exploitation. And probably given the time t is exponential of 1. And what is the probability that will be exploited before a bug is fixed? Oh, so we have e given t. So we have given the time t, the exploitation follows this distribution. So this is before a bug is fixed. So it is just, so we need the probability of e. I cannot define exploitation exactly, right? So what is exploitation exactly? What does E tell you? Tells you a probability that exploitation will happen? No, it's like I don't think you should write this at all, right? You just have a probability of E, exploitation happening, given that the time is 1 minus e to the t, so probability that exploitation before a bug is fixed. So for it to happen, you need first to find, given that it doesn't find, so idea is that it's the same formula. So you have, given that it doesn't find in that time, so for each, so you have, so p of exploitation happening is so p, let me write it here, is integral from from 0 to infinity, I guess. You have the integral from 0 to infinity, and it is the integral of p given, you have it here, so it's like p of e given t. Let me just take it from here so I don't have to, right? And then this is p of e, t equals to some time, and we have f of t equal at that time, and then we have dt. Well, what is this equal to? Well, let me just take it. Well, this is equal to integral from 0 to a big number, because it doesn't calculate infinity, that's supposed to be a very big number. And then you have 1 minus e to the power of t, and then you have for t greater than 0, because, well, this is from, if you think about this, is from minus infinity to infinity. And then you have from 0 to a big number, well, it is infinity, and then you have times to a minus t times this, which I will just take from this, dt. It gives me a big number, I guess. Does it go bigger? Yeah, it goes to infinity, so it's not good. The bigger. So I made a small mistake, probably. From 0 to 100. That's just a big, I made a mistake, right? This number. So. But I think I get the solution. I'm pretty close, because the time in which the security bug is detected has this distribution. And then for each time, for each one, the probability of it happening is 1 minus e. So you have like a tree. So the point is that you have a tree, and the probability of the tree happening is, oh, but this is f of t, the distribution of t, right? This is not, I should integrate this, exactly, because I need f of t of t. Well, we know this is just, what's this? This is exponential. This looks like the normal one, but not really, like the normal distribution, but not really exactly like the normal. You have 1 minus something, which looks like a normal. Why is this at f? That's pretty weird, but you're saying this is f, right? And it has 1 over 2. That is not a norm. Can I derivate it? But it says that the integral of probability sought can be transformed into an expression with a value that can be read from a normal distribution table. So that's what concerns me, because here I need to find the derivative of it. Oh yeah, I can find the derivative of this pretty easy, because it's just, well, 1 minus e minus t squared over 2, and I need to find derivatives is 0 minus 1. The derivative of this is, yeah, you have plus t, so it's t e to a minus t squared over 2. So this is just, so if I want to do it real quick for f of t, then I have plus in here, I have t in here, and then subtract. And then here, when I multiply it here, it's just t, and I get the right solution, exactly. But now the point is, because the idea is that for each exploitation, you have a value of t, and each the probability of an exploitation happen here, so not happening and happening, but the probability of an exploitation happening is 1 minus e to the t. So you need, for each one of these values, you need to apply this probability and then add them all up, and that's just the integral of this two multiplied the thing with thing multiplied together. So you have a probability of e given t, this thing, times of f of t dx over all the region where it's defined. This is the probability of an error happening. This is like the total law of probability, but in continuous form. And it is that, so we just do this here. So you have this here, so this, and how do I break this into an easy expression? Well, this is t e minus t squared over 2 minus t e minus t squared over 2 minus t. Somehow they said you can bring after a partial integration, so we need to do a partial integration of this. That's what? Partial, am I right what a partial integration is? Yeah, this is the partialization. I am right. What? You can bring that? Oh yeah, I think so. Oh yeah. So yeah. So what this is actually is just some partial integration. Okay. So we have du, and du is equal to 1 minus e to the minus t, and then we need to integrate this. We are not integrating this already. Do not integrate this. What should we derivate? It's good to derivate that one. So what we do is that, right, we do 1 minus e to the minus t dt, and we do the t e minus t squared. No, we do t e minus t squared over 2. No, that's the integral for that. So I was right. So we do 1, and we derivate this, and we get e to the minus t for the derivative, t. And then you get the integral, so you get t e minus t squared over 2 dt, and you need to integrate it. And then if you integrate it, well, I have no idea what that integral is, do I? Well. This is actually pretty weird. So the point is the integral of this. Yeah, if you integrate this is just, yeah, we had this earlier. This is 1 minus e minus t squared over 2. So overall, this is just e to the minus t, 1 minus. Yeah, what was the point of all of this? No, it's this. I don't fucking see that though. Yeah, I'm pretty sure that's the right answer, but how do you do a partial integration to find that? What is function? Well, so the integration of this is just, so I know the integration of this, right? So e to the, from 0 to infinity minus. Maybe I see that you need integration. Yeah, I can see you need it. It's like so it's just a simple integration by parts. This is not a, and how does the normal, and I also forgot the normal, you should know it. You see, it's not even close. I mean, all of these. What do they? So there is a man standing on Hero Square. So we have a man and he's standing at Hero Square with a phone that is transmitting a virus, and his phone is nearby. A tourist stops to photo and spends. Okay. So I cannot I can calculate it like this, but I cannot like do a partial integral and look for this function in there. If something doesn't come out, I'm probably doing some mistake. But yeah, probably doing some mistakes, but I'll see, I'll ask the professor. So there is a man standing at Hero Square, so we have a Hero Square with a phone transmitting, okay, nearby a tourist stops to take a photo. Spends a uniform distributed amount of time, okay, measures in minutes from the interval 1, 2 to 3 or 2, and then moves on. If a tourist spends time taking pictures, there is a T, so if a tourist spends, there is, it's the same idea, T and a probability that his phone will catch the virus. What is that his phone will catch the virus before it moves on. So let's call it T. It's the same like exercise, right? So we have 18 dot, and we have this. Oh my god, I should do right, and then we have T the time, and the tourist spends, time the tourist spends, and then we have let's call it virus, given the time, the probability of virus, given that the time is equal to T, is equal to T minus T or 1 over 2. You can just like do it real quick. T over 2 T over 2 to power of 2, and then T minus T minus 2, and T here, T is a normal distribution of, no, it's a uniform distribution between 1, 2 and 3, 2. So we know that f of x of the interval, so we know that f of x of t is just equal to so f of x of t is just 1 over 2 plus it's 1 over it's just 1 over 1 3 over 2 minus 1 over 2 3 over 2 minus 1 over 2 is just 1. Is the distance 1? Yeah, the distance is 1. No, the distance is 2 or 1. The distance between 1 over 2 and 3 over 2 is just 1. So it's just 1 in the region 1 over 2 and 3 over 2. Well, we can do this, I guess. In this region, and then we have virus, catch virus given this, so now we use a law of total probability. So P of V catching a virus completely. Oh, what is the problem? She just gave us a problem. She's just asking about this. Because it's saying there is a probability that his phone will catch the virus in that time span. And wait up. Yeah, in that time span. So what is the probability that his phone will catch the virus before it moves on? Is this? This is like before it moves on, there's a probability that it will catch the virus. And the general probability is just that it will catch the virus is and you just need to write this. So it says whether we catch a virus is integral from the law of total probability, but we don't care because now we have a uniform distribution, so it's 1 over 2 to 3 over 2, and is the probability of t minus t squared over 2, and times 1 times 1, just for good measure, dt. And I can just calculate it down here real quick. I can use, why is this not calculating, what is the error? We end with an integration variable like it is, ending with dx, rather than ending with dt though. Does it recognize? And this is what I got, and they got 1 over fucking 3. And 1 over 3 is not even close. So what did I make mistake in here? Well, this is probability to catch a virus. What is it asking for? So there's a man standing at Hero Square with a phone that is transmitting a virus. Nearby a tourist stops to take a photo, span a uniform distribution amount of time. I don't know, what? So it's asking for Gemini. So what is the probability that this phone will catch before it moves on? Well, it's this right here. It's from 1 over 2 to 3 over 2, right? And then you have, why did I do, I can just remove this, okay, and do times 1 like this, comment. And then it is 1. Are you sure that f of t is 1? Because this is not t squared, this is just t of 1 over 2. It's just 1 over 2 squared. I'm just t squared. I can just do this. Yeah, and this is 0 and 3. I mean, you can calculate it real quick. You can see it is. Yeah, you can just calculate. It's equal to 1 over 3. We have it. Nice. And that's all for this. This one is finished with some particular questions. So the questions I had for this were, so I will just write my questions here real quick. So question 1, so then questions at the end. Just write questions. No, I don't want questions at MD. Just want questions. Right, I want question 1. 7.b plus 7 over 2 this is what I did yesterday. I can just, right, and then the next questions, I don't think so, right? Yeah, for the 12th one. I don't see what. Sure. 17. How do I big omega. Big omega. No, it's not omega. It's big phi, maybe. Phi. I just put the question in the beginning. It makes so much more sense. Yeah. Something wrong here. Can't I see 12? So weird. Why should I do this? What? Maybe I should just do this. It's so much cleaner. Then do the line. No? Okay. Wait, and then do 1, 2. Yeah, I should do that for each one of them. Okay, so I'll just write to my professor to this. I'll ask him these questions exactly. So we finished this exercise set. So I think we need to do the new one, the 11 one. Okay, nice. There. Oh no, we have the Chebyshevs now. Oh, we have the inequalities. Where have I put the inequalities? I have a big mess of things right now. We also need to do 9. Should be the 9. Let's do 9. Let me do the Chebyshevs. Oh my god, so many things, right? So many things. 4, 3, 1. And we have a 10 for 3 here. The 11 one is missing. And we have X for the test. Let's do 9 because I'm left far behind at 9. So I'm going to do this one. So apparently I have done only one in this exercise. Oh, you don't have a lot in here, you only have 10 questions. See how fast we can. Okay, recitation 10, so let me download the station file. Station 9. Oh, here. Yeah, Teams is the worst app there exists. How hard can it be to just write a good app? Dead. It's not even there. Funny. Well, I think I'm just gonna end the stream because it's been a long time. Probably it's 3 hours of recording, so yeah. So I think, and oh, it's 30 FPS. Oh, I think I'll fix it and make this 60 FPS this time. Okay.